Back to Calc 2. Today we're looking at lesson 10.3 using the integral test. First, let's define what are non-decreasing partial sums. So let's suppose that we have the sum of a series that goes from n equals 1 to infinity of a sub n is an infinite series with a sub n greater than or equal to 0 for all n. Then each partial sum is greater than or equal to its predecessor because the sum of the series has to equal to the sum of the previous n terms plus the next term. Therefore, whatever we get for the partial sum with the first term has to be smaller than the second term. Or as we keep adding terms, each term has to be greater than the previous term. Since this partial sum forms a non-decreasing sequence from lesson 10.1, the monotonic sequence theorem says, which gives us corollary of theorem 6, a series then with a summation from n equals 1 to infinity of a sub n of non-negative terms converges if and only if its partial sums are bounded from above. So again, think about if we keep adding terms, those terms have to eventually go to 0. The change in the terms has to go to 0, but it also has to be bounded above by some upper bound m. For example, let's consider the harmonic series. So the sum of n equals 1 to infinity of 1 over n is the series 1 plus 1 over 2 plus 1 over 3 all the way up to 1 over n on to infinity. So even though the nth term goes to 0, the series is not bounded from above for the sequence of partial sum. We'll show this in another problem. We'll show this right now. So let's break up our series so that we have 1 plus 1 half plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8. So as we look at the partial sums, we're going to notice that we're going to get a 1 plus a 1 half. The value we get for the 1/3 and the 1/4 has to be greater, because 1/3 is bigger than 1/4, has to be greater than 2/4, which is also equal to 1 half. Same thing for 1/5, 1/6, 1/7, 1/8. That has to be greater than 4/8, which is also equal to 1 half. Therefore, that sum has to be greater than 1 over 1 plus 1 over 2 plus 1 over 2 plus 1 over 4 plus 1 over 4 plus 1 over 4 plus 1 over 4, so on and so forth. That converges. This converges. This one does not. So this diverges. So the harmonic series, which again is this series, it's also what we did in a previous lesson, I think in chapter 8, lesson 8, 1 over p to the n, 1 over n to the p would be, there's 1, and so again that's got to diverge. So we're going to take a look at the integral test. To do that, we're going to look at this problem. Problem that's related to the harmonic series, but whose nth term is 1 over n squared instead of 1 over n. So for example 2, again, we're going to use the integral test, and that means we're going to take our summation and turn it into an integral. And so we want to compare this with now the integral from, we'll have the same bounds, 1 to infinity, but now we're going to switch our n to be a function, so we have 1 over x squared dx. So let's recall then our function f of x will be 1 over x squared. Therefore, recall then our sequence then is 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared all the way up to 1 over n squared. Therefore, we can think of this to get our function. This then would be f of 1 plus f of 2 plus f of 3 all the way up to f of n, and that continues. We can look at a graph. And so at 1, we're at 1. So we're kind of looking at the partial sums of the rectangles. Then we're at 1/4, 1/9, 1/16. We want to look at a underestimation. So we want to kind of look at these points. To do that, we're going to leave in the first term then as f of 1. And then we're going to add then the integral from 1 to n of 1 over x squared dx. So we want an underestimation because, again, we're looking for bound from above. Therefore, we're going to get 1 plus the integral from 1 to infinity of 1 over x squared dx. That should have been an infinity up there, which we've worked that one out before. And so this has to be 1 plus 1, which is 2. Therefore, the partial sums are bounded from above by 2, and the series converges. But we have to be careful here. Sorry, backed up. Wrong theorem. So because the sums converge, because the partial sums converge, or because the integral converges, then the series converges. That takes us to theorem 9, the integral test. Let a sub n be a sequence of positive terms. Suppose that we can set the sequence equal to a function where f is continuous, positive, decreasing function. So we have to meet those conditions of x for all x greater than or equal to capital N, where capital N is a positive integer. Then the series, the sum from n equals n to infinity of a sub n, and the integral from n to infinity of f of x, either both converge or both diverge. And that we're going to call that theorem 9 our integral test. Therefore, example 3, show that the p series converges if p is greater than 1 and diverges if p is less than or equal to 1. So I'm not going to go through this one. This one's in the book, and this one's a pretty lengthy proof, but you can read through that one in the book. But notice here then, if p is equal to 1, we get our harmonic series, which we looked at in a previous problem. That takes us to example 4. The series, the summation from n equals 1 to infinity of 1 over n squared plus 1 is not a p series because we have the plus 1 there, but it converges by the integral test. The function f of x equals 1 over x squared plus 1 is positive, continuous, and decreasing for x greater than or equal to 1. So let's look and see what happens with that summation. So we're going to rewrite this then as an integral from 1 to infinity of 1 over x squared dx, because that's the equivalent function, and I missed my plus 1 there. So I want to go back and get my plus 1. So x squared plus 1 dx. But now we have to evaluate a limit going again to infinity. So we're going to take the limit as b goes to infinity, then of the integral from 1 to b of 1 over x squared plus 1 dx. If we add a squared on the 1, we're going to recognize that as tangent inverse. So now we get the limit as b goes to infinity for tangent inverse of x evaluated between 1 and b, which then is the limit as b goes to infinity of tangent inverse. We'll evaluate the upper bound first, b, minus the lower bound, which is tangent inverse of 1. Well, we can go back to our tangent inverse functions and the graph of tangent inverse, and know that as tangent inverse goes to infinity, we're reaching the upper bound of the graph, which occurs at pi halves. So we get pi halves, that's an asymptote for the tangent inverse function, minus tangent inverse of 1, well, that's pi fourths. Therefore, we get a value of pi fourths. Therefore, we get a value that's less than 1. So pi, or 3.14 divided by 4, is less than 1. So the series converges because pi fourths is less than 1. But, got to be careful here, pi fourths is not the sum of the series. Next up is example 5. Determine the convergence or divergence of the series. Letter A, we have the sum from n equals 1 to infinity of n times e to the negative n squared. Let's first of all rewrite that, noticing that f of x then is n over e to the n squared. So we're going to write that as an integral from 1 to infinity of x over e to the x squared dx. We're going to do a change of variables on this one. We're going to actually use u substitution. So let's set u equal to x squared. Then du is equal to 2x dx. And so now we're going to have the integral from 1 to infinity of, notice here our x dx will cancel, leaving us our du. So we get e to the u. The x cancels on top, but we're left with a 1/2 because we need to divide by the 2 to make this 2 cancel. So we can take that out to the front as a 1/2. And then we have 1 over e to, the integral from 1 to infinity of 1 over e to the u du with our constant out in front. Now we can recognize that we have an indefinite integral, so we're going to take a limit. So we have 1/2 times the limit as b goes to infinity for the integral from 1 to b of 1 over u squared du. That gives us then, now we can evaluate 1/2 times the limit as b goes to infinity. Remember, 1 over u squared is u to the negative second. We're going to add 1, so that turns into u to the negative first, which is 1 over u. But then we need to divide by a negative, so we get a negative 1 over u. And we're going to evaluate that between 1 and b. Therefore, we're going to get the limit as b goes to infinity of, if we plug in b, we're going to get negative 1/2. I'm going to multiply the 1/2 back through, so negative 1/2 e to the negative b plus then 1/2 times e to the negative 1. Notice then as b goes to infinity, this is going to be 1 over e running out to infinity. That's going to go to 0. So we're left with this term, which has to be then 1 over 2 times e. Therefore, because this value is less than 1, then our integral converges. Therefore, the series has to converge. There's our integral test. Part B, we're going to evaluate the integral from n equals 1 to infinity of 1 over 2 to the ln. So again here, our function, f of x, then will equal 1 over 2 ln of x. So we're going to rewrite this as an integral. So we're going to want to find the integral from 1 to infinity of 1 over 2 ln of x dx. Here we're not going to do u substitution. We're going to do a change of variable just to make this work a little bit better. And to do that, we're going to set u equal to ln of x. And then we're not going to take a differential of this equation. We want to rearrange this one and then use our u substitution kind of as a change of variable. So we're going to either think about this as taking an e to both sides, Or you can think of, and if we do that, e to the ln of x, e and the ln cancel, leaving just x. Or you can rewrite this as log base e to the x and use the circle pattern to go back to the exponential form. Either way, now we're going to take the derivative. So the derivative of e to the u is e to the u du is equal to dx. So now we can rewrite this as the integral from 1 to infinity of 2 ln of x becomes then 2 to the u, and then dx is equal to e to the u du. So we'll put the eu on top, and du goes on the bottom. We'll notice that these are both to the power of u, so we can rewrite this then as the integral from 1 to infinity of quantity e over 2 to the u du. Now we can use our indefinite integral, so the limit as b goes to infinity from 1 to b of e over 2 to the u du. For that, we need to use our integral for a power function, and that's going to be then the limit as b goes to infinity of 1 over ln of e over 2. Again, that's just a constant. And then we have left e over 2 to the b to the u. And we're going to evaluate that between 1 and b. So that leaves us then to work out our final solution, the limit as b goes to infinity of 1 over ln of e over 2 times plugging in our b for the u. We get e over 2 to the b power minus e to the 1 over 2 which is minus 1. That doesn't seem right. Regardless, I think that should be e over 2. What's going to happen then as b runs out to infinity, this term then is going to take off to infinity, so then our integral will diverge. Therefore, because the integral diverges, therefore the series will diverge. And that is using the integral test. Last thing we're looking at is the bounds for the remainder in the integral test. So suppose we have a series as a sequence of positive terms with a sub k is equal to a function where f is a continuous positive decreasing function of x for all x greater than or equal to n, and that the sum of the terms of the sequence converges to some value s. Then the remainder, r sub n is equal to s minus s sub n, satisfies the following inequality. Here to the right, we have an overestimation. And then with the n plus 1, we're going to get an underestimation. And then the actual value r sub n will be somewhere in between. If we add the partial sum, s sub n, to each side of the inequality, then we get this formula. This inequalities are useful for estimating the error in approximating the sum of a series known to converge by the integral test. The error can be no larger than the length of the interval containing s, with endpoints given by this formula. So let's look at an example of that problem with example 6. Estimate the sum of the series 1 over n squared using the inequalities in 2 and n equals 10. So first we need to find a way to calculate this sum of the series. So we're going to write that as an integral from n to infinity of 1 over x squared dx. Again, because we're going to infinity, we have to write the indefinite integral, so that is the limit as b goes to infinity from the integral into b. Then we can do that We can evaluate the limit 1 over x squared. Remember, that's x to the negative second. We're going to add 1, so that's x to the negative first, which is 1 over x. But then we need to divide by negative 1, which makes this negative. And I messed up. So we're evaluating that one for between n and b. To do that, then we're going to get the limit as b goes to infinity of, if we plug in b, we're going to get negative 1 over b minus negative turns into plus, then 1 over n. But if b is running off to infinity, this term goes to 0. Therefore, the integral from n to infinity of 1 over x squared dx has to equal 1 over n, which we're going to use to solve for our error. Now we're going to use the formula up above to figure out the error. So for n is 10, then we're going to have the sum s of 10 plus the integral from 10 plus 1 is 11 to infinity of f of x dx is less than or equal to s is less than or equal to s of 10 plus the sum from 10 to infinity of f of x dx. It might seem counterintuitive that the 10 is on the right and the 11's on the left, but remember this thing is getting smaller even though we're going up another term. So, and we'll see why here in a second. So now we can evaluate s of 10. We have a formula for these integrals, and that is 1 over n. And so that is going to be, in this case, 1 over 11 is less than or equal to s, is less than or equal to s of 10, plus, using our formula, plugging 10 in for n, we get 1 over 10. And again, it seems counterintuitive, but here we see that 1 over 11th is indeed smaller than 1 over 10. We can work out then with the calculator s of 10 is equal to the sum of n equals 1 to 10 of 1 over n squared. Your graphing calculator has that application. So when we do that math, we get 1.64068 is less than or equal to s is less than or equal to 1.64977. Finally, to get the error then we're going to use the midpoint of those two values. So we'll add and divide by 2. Therefore, the value for the sum of n equals 1 to infinity of 1 over n squared is approximately 1.6452. That is lesson 10.3, the integral test for Calc 2.